Hello everyone. Today we are going to learn about the fundamental theorem of arithmetic. So let us start with it. Let us first read the statement of it. But before starting with the theorem or the statement part of it, I would just want to brief you about something that's related to this theorem. Now the statement of the theorem does mention about the word arithmetic. What does the word arithmetic in general means? So arithmetic always corresponds to different numbers or dealing with set of numbers using variety of operations. Now we all know that when you talk about numbers in general, they are divided into various groups. For example, we have the composite numbers, we have the prime numbers, we have even numbers, we have odd numbers. So arithmetic basically deals with all of these numbers. Now let's start with this theorem, which is the fundamental theorem of arithmetic. Now before starting again with this theorem, I would just want to tell you what would be the agenda for today's class. So we are first going to see the statement of the theorem. Then we are going to move on to the solving factorization problems. We are going to solve problems of LCM and HCF using this theorem. Then we are going to derive a property related to LCM and HCF. And after that, we are going to see certain real life applications of this theorem. Of course, when we are solving different types of problems, we are using this theorem already in mathematics, so that would be the math application part of it. Likewise, we are also going to see real life application of this theorem. So let's start with the theorem. Now the statement of the theorem reads as follows, that every composite number can be uniquely expressed as a product of primes except for the order in which they occur. Now first of all, whenever a statement or any theorem or proposition comes to you, you first need to identify the subject in that theorem. So here, for your knowledge, the subject or the main, you could say the main factor here is the composite number. So here we are dealing with composite numbers. I hope you all know what is a composite number. Just a quick revision, that any number which can be factorized or which has factors apart from the number itself and 1 is called as the composite number, whereas a number whose factors are just the number itself and 1 is called as a prime number. So this theorem particularly deals with composite numbers and their representation. So what does it say? That every composite number can be uniquely expressed as product of primes. As of now, I would just want you all to focus on this part of the theorem. Again, I'll tell you, there are just three main short phrases that you need to keep in mind. That this theorem is about composite numbers and its representation. And how can you represent a composite number? You can represent it uniquely as product of primes. Now again, the word uniquely plays an important role. Why? Let's say you have a number 6. Okay, now we can represent it in terms of prime numbers as 2 multiplied by 3 or 3 multiplied by 2. But here too it is given that every composite number is uniquely expressed. But here if you see, you have got 2 representations of the number 6. How is this even possible? So the answer to my question lies in the other part of the statement. Here they say that even though we know that a composite number is can be expressed, it can have multiple representation except for the order in which they occur, meaning irrespective of the orders of these prime factors, you're going to consider it as the same representation. So it doesn't matter whether your 2 comes first or your 3 comes first, you're going to consider it as the single representation until and unless you don't find any other representation apart from this. So I hope you're clear with the statement. To once again revise the statement, I would tell you that this theorem is about composite numbers ka representation. This representation is unique in nature, and how do you represent? It is represented in terms of product of primes. And the second part of the statement, which is equally important, is that except for the order in which the prime occurs, meaning 2 into 3 is same as 3 into 2. The order of the numbers doesn't matter in this case. So I hope you are all thorough with the statement now, and you would keep these three things in mind. That is all with the statement part of this theorem. So let's say in general, if you want to represent a composite number, so let's say x is a composite number. So this composite number can be represented as p1 into p2 into p3 and so on multiplied by pn. Now what are these PIs, P1, P2, P3 and so on up till Pn. What are these? These are nothing but the prime factors of the number x. So I can say that here P1, P2 and so on up till Pn are nothing but the prime factors. And these prime factors would of course be of the number x. So this is how you would generally represent a composite numbers in terms of their prime factors. Now let us actually write a number in terms of its prime factorization. So here the number is 148. We have been doing this since I think you have already done it in your 8th standard, 9th standard, and again you're going to do it. You would understand why are you doing it, like how more in advanced manner you can use this theorem, but as of now we are going to start with the basics only. So we have 148 as the number with us, and the question says factorize this number. So of course I'll be using the normal method for factorization. 148, we know that we have to find the prime factors, so we are going to start with 2. So this becomes 74. Now again this number comes in table of 2, so 2 into 3 and 7, then 37, ones are 37. So if I want to write the prime factorization of this number, it would be 148 is equal to 2 into 2 into 37, which is nothing but 2 square into 37. So if at all you are asked to write prime factorization of any number, what you are supposed to do is, you are supposed to come up with this kind of representation, wherein first thing what you would do is, you would find the factors of that number. You're going to write them in the multiplication format. You're going to arrange those factors in ascending order, meaning from small to big. Here we just had two different factors, 2 and 37. So the arrangement was pretty simple. But for presentation purpose, we would say, of a clarity purpose, at a glance, you have to, or you should actually place the factors in their ascending order and try to club the similar factors, meaning 2 into 2 I have written it in terms of powers. So you have to write the factors in terms of powers and also in the ascending order, meaning small to big. So this is how you are going to factorize any number. Now this is something that you have been doing since your 8th standard, and this is a pretty basic question. Where are you going to use this theorem? So we are going to use this theorem to find LCM and HCF using prime factorization method. So if at all the question comes in exam, find LCM and HCF using prime factorization method, you are going to use this method to first find the factors of the given numbers. They can be in pairs or triplets also. That is, you would be getting either 2 numbers or even 3 numbers whose LCM and HCF you are supposed to calculate. And then after finding out the prime factors, you can come up with the answer for LCM and HCF. So the question here is, find LCM and HCF of 8 and 42. Let us first visit the definition of LCM and HCF. So here if you see, I have written what is LCM and what is HCF. Again, this is a concept from your lower standards, so we are just going to revise its definition. Now, as the acronym suggests, LCM meaning least common multiple. So what is LCM? It is the product of the greatest power of each prime factor. So you have been given 2 numbers. What you are supposed to do is whatever prime factors are there, okay, you are supposed to take the greatest power of those prime factors of all the numbers and you are supposed to multiply it. Verbally it may find little abstract, but once I solve it on the board, you will of course be able to understand it. So this is what LCM is. What you are supposed to do in LCM? You are supposed to write it as the product of greatest power of each prime factor. Now comes the HCF, that is the highest common factor. Now here if you see, here also you are going to write it as the product only, but here you are going to write the product of smallest power of each common prime factor. So in HCF, you are first going to find out which common factors are there between the two numbers or three numbers, and you're going to write its smallest power. You will understand it. I'll show it to you. I'll explain it to you. So we have two numbers, 8 and 42. The first step is in LCM and HCF is to write its prime factorization. So let's start by writing its prime factorization. 8, of course, it is cube of 2. So we can write it as 2 into 2 into 2. So 2 into 2 into 2. So that is equal to 2 cube. Now 42 can be written as, it is 6 into 7, but again we can write 6 as 2 into 3 into 7. So we can write it as 2 into 3 into 7. In terms of powers, it would be 2 raised to 1 into 3 raised to 1 into 7 raised to 1. Now we are first going to find out its LCM. So LCM of 8 and 42. So here if you see, what does LCM says? The definition of LCM is, it is the product of greatest power of each prime factor. So now here if you see, 8 has prime factor as 2 and its greatest power is 3. Right? There is no other prime factor here, just 2, and its greatest power is 3. So you are going to write 2 cube multiplied by, already we have taken 2 as the power of the greatest prime factor. Now you are going to move at the other prime factors in the next number. So then we have 3 and we have 7. Maximum power of 3 is 1 and maximum power of 7 is also 1. So you have 8 into 3 into 7, which is 24 into 7, and the answer for this is 168. So I'll again explain these to you. What I have done is I have written the prime factorization of 8 and 42. 8 is written as 2 into 2 into 2, which is 2 cube. 42 is 2 into 3 into 7. Basically it's 6 into 7, but we can factorize 6 further as 2 into 3. So we have we wrote it in the power form, which is 2 raised to 1, 3 raised to 1 and 7 raised to 1. Now by the definition of LCM, what we are supposed to look at is that you are supposed to see the greatest power of each prime factor. So now here if you see, the prime factors total are, we have 2, we have 3 and we have 7. So what is the greatest power of 2 over here? It is 3. So you are going to write 2 raised to 3. What is the greatest power of 3? It is 1. So 3 raised to 1. What is the greatest power of 7? It is again 1. So we have written 7 raised to 1. We know it's 8 into 3 into 7, so that's 24 into 7, and 24 into 7 is 168. So the least common multiple of 8 and 42 is 168. Now similarly, let us find HCF of 8 and 42. So HCF of 8 and 42 is, now again pay attention, you have to be very careful with LCM and HCF. In HCF, what you are going to do is you are going to first see which are the common factors. So here if you see, 2 is the only number that is common in both of them. Can you see 3 over here in the factorization of it? Of course not. Can you see 7 in the factorization of it? Of course not. So you are going to, so if you see, it is 2 which is the only common factor that is there between these two numbers. So as here if you see, common prime factor between 8 and 42 is 2, and you are going to take the smallest power of it. So in the first number the power is 3, whereas in the second number the power is 1. So which is the highest common factor between 8 and 42? It would be just 2. So the HCF of 8 and 42 is 2. I hope you're clear with this problem. Okay, you'll get more clarity in the next problem. The next problem is you have to again calculate the LCM and the HCF of 45 and 60. So let's start. We will first write the prime factorization of 45. So that is again 9 into 5, but we can write 9 as 3 into 3. So 3 into 3 into 5. In terms of power, it would be 3 square into 5 raised to 1. 60. 60 can be written as 12 into 5, right? So, but 12 we can write it as 6 into 2, where 6 can be further written as 3 into 2. So the prime factorization for 60 is 2 into 2 into 3 into 5. 2 2s are 4, 4 3s are 12, and 12 5s are 16. In terms of powers, you can write it as 2 square into 3 raised to 1 into 5 raised to 1. Now pay close attention to how I calculate the LCM. So the LCM of 45 and 60 would be, you're going to see what are the possible factors here. So here if you see, the possible factors are 2, 3 and 5. Okay, from here we get 2, 3 and 5, here 3 and 5. So we are just going to write the common factors only once. Okay, that is why I've written 3 and 5 only once. Now what is the greatest power of 2 over here? You're absolutely right, it's 2. What is the greatest power of 3 over here? Here it is 3 raised to 1, whereas here it is 3 raised to 2. So we are going to take 3 raised to 2. Whereas the power of 5 in both the numbers is 1 only. So the LCM of 45 and 60 would be 2 square into 3 square into 5. So that is 4 into 9 into 5. So we have 4 into 5 is 20, and 20 into 9 is 180. So this is the LCM of 45 and 60. Now let us calculate the HCF of 45 and 60. For our LCM, what we have done? We have taken all possible prime factors and we have taken the greatest powers of those prime factors. For HCM, HCF, we are going to take the common factors. So now viewers, can you tell me which are the common factors over here, or what common numbers do you see in both these numbers? You're absolutely right, it's 3 and 5. So 3 and 5, can you see both these numbers in the prime factorization of both the numbers? Right. So 3 is there and 5 is there. Now in case of LCM we were taking the greatest power, but in case of HCF we are going to take the smallest power. So what is the smallest power of 3? In one number we have 3 ka square, and in the second number we have 3 raised to 1. So which of this are we going to choose? 3 raised to 1. You're absolutely right. Similarly, you have 5 raised to 1. So the highest common factor over here is, we have 3 into 5, so that is 50. So this is the HCF of 45 and 60. Now students, we have calculated or we have learned how to calculate the HCF and LCM of two numbers using the prime factorization. I would want you all to make a quick observation so that we would come up to a very interesting property related to HCM and LCF. I would want you all to find the product of the LCM and HCF that we have got. So, let us calculate the product of LCM and HCF of 8 and 42. So, we all know that 168 into 2. So, we have 8 2s are 16, 2 6 are 12, 13, 1. So the answer is 236. So this is what the product of LCM and HCF. Okay, likewise, let's calculate the product of the numbers whose HCF and LCM is calculated. That is 42 multiplied by 8. So we have, I'm so sorry, it's not 236, it's 336. Okay, so we have 42 into 8, so 8 into 2 is 16, 1, again 4 8s are, it's 4 8s are 32 plus 1 is 33. Now students, I want you all to observe and tell me, what do you see? If you see, you get the answer 336 over here, you get the answer 336 over here. Hold your horses. Let's try it for the next problem as well. But again, I want to tell you what exactly we did is that we took the LCM and HCF of the two numbers and we multiplied. We got the answer as 336. Similarly, we took the numbers now and we multiplied them. We got the answer as 336. Now, let us see what happens for the next pair of numbers. So, we have the LCM as 180 and the HCF as 50, right? So when you multiply both these numbers, so we have 5 zeros or 5 8s are 40, 900, so that's 2700 is the product of LCM and HCF of 45 and 60. Now let us calculate its product. So 60 into 45. Calculate the product of both the numbers. Okay. So again 300, 0, 4 into 0 is 0, 24. What do you observe? Again, here if you see, the product of the LCM and HCF of both the numbers is 2700 and product of both the numbers is again 2700. So what can you conclude with this? I'll tell you. Can we say that, let's say that you have two numbers A and B. For any two natural numbers A and B, the product of HCF of A and B and LCM of A and B would be equal to the product of those numbers itself. Is this true? Yes, of course, it's true because we have just verified it. Again, my dear students, you can use this property to actually verify whether your answer is correct or not. Like you calculate HCF, you calculate LCM, take uska product and then take the product of those two numbers and see whether both the answers are same or not. If both the answers are not same, it means that you have done some mistake in the calculation of your HCF and LCM. So this is a very, very important property which is actually used not only to verify your problems, but you can also use it in elsewhere. Meaning, let's say you have been given one number and you have been given the LCM and HCF of the two numbers, and if you are asked to find the number, can you easily find it? Of course, because here if you see, this is just like finding the missing quantity. There are total 4 quantities. We have the HCF, LCM, A and B. Now since we don't know what is B and we know the 3 quantities over here, can we easily find the value for B? Of course, we can find it. I'm leaving that up to you because I'll be testing this in the evaluation section for sure. Now let's move on to the third part, that is actual application of this theorem in one of the application based mathematical question. So here the question says you have to prove whether the given number, meaning this number, is composite or not. So how are you going to do this using the theorem? Once again, I would want to revise the statement of the theorem. It's about composite number ka representation. And how are they represented? Uniquely plus product of primes, except for the order in which the prime occurs. So if we show that this number can be expressed as product of primes, then can I say that this number is composite? Yes, of course. Why not? Because if we are able to express the number as product of primes, about who this property is true? This property is true, of course, about the composite number. So then we can easily conclude that the number, the given number, is a composite number. Now you might say that, looking at it, it does look like it is expressed in terms of composite. It is represented in terms of prime numbers. But here, if you see, here you have multiplication, but here there is an addition symbol. So our aim is to eradicate or to remove this addition ka symbol and just represent the number in terms of product of primes. So we are just going to use basic math steps. So what we are going to do is, this is one term and this is the second term. Now both these terms do have one number in common, and that is number 13. So we are going to take it common. Okay, so we are going to write 13 outside the bracket. So what's left inside the bracket? You have 7 into 11 into 1 plus 1. First, by BODMAS rule, we are going to perform multiplication. So we have 7 into 11 into 1, so that's 77 plus 1, so that is 13 into 78. Now, am I going to proceed further? Of course not, because what the theorem says, that if a composite number is supposed to be expressed as product of primes. So are we getting product? Yes. Now, is this product of primes? Of course, it is product of primes. So here we can say, hence the given number is composite number. Okay. You might say that, but number 78 is not a composite number. Of course, it's not a, I'm so sorry, it's not a prime number. Of course, it's not a prime number. But can you write the prime factorization of this number? Right? I would want you all to tell me the prime factorization of number 78 in the comment section. So, this would be written as something into the prime factorization of 78. And then we can say that since the number is expressed as product of primes, hence it is a composite number. So, we have seen the statement, we have seen, how you can use it to find LCM and HCF, how you can use it to actually show a number, how a number is a composite number. Now let us move on to the real life application of this theorem. So, where can you actually use? There is one, particular area which is called as cryptography. Now, what is this cryptography? We all have this habit of texting, we all have this habit of sending formal emails, various messages to our friends or to our teachers or anybody. So, when you send this message, it is very likely that you are intending it to send to one person, but that there would be someone who would enter between this part and try to see what you are actually sending. Right? So cryptography is an area, or you could say it is basically a concept which is used to actually keep your information safe with the help of secret codes. So what you are going to do is, whatever information you are sending to your friend, you're going to hide it under a secret code. That is what cryptography is. Basically, it is a method to keep your information safe, to keep your information from getting accessed by anybody else whom you don't want to get accessed it by. Right? So I'll explain it to you. Let's say there is a person A and there is a person B. Now person A wants to send something confidential to person B. Let's say that he wants to send an important some important study notes, okay, to person B. So what he is going to do is he is going to actually send it through messages. Okay, now what cryptography does and how it is related to, you know, this theorem. This person is going to lock this message using the number 55. Now this entire system, okay, this has been known only to these two people and it's not known by any other person, be it C, D, E, F, G, anybody. It's not known by any of them. This system of encryption or of hiding the information is only known by both of them. Okay, so A is telling to B that see, I'll be sending you my notes today, but I will be locking them. So how is he locking them? He is locking them using the number 55. So whenever anybody tries to open this message, they are just going to see the number 55 because that is the lock of that message. So if anybody tries to open that message from other devices, right, so using certain kinds of hacks, you know, so if that person clicks on the message, he's just going to see number 55, not going to see what is there inside it. Now 55 is the lock, but then what is the key for this number 55? B knows that here A has used prime factorization of 55, meaning we know that 55 has got unique prime factorization. There cannot be any other number that can be used as prime factorization for 55 apart from 5 and 11. So of course, the key for 55 is its prime factorization, that is 5 and 11. So when the message reaches person B or student B, what he is going to do is he is going to open the lock using the key 5 and 11. This is one area where, you know, this theorem is used, but there are multiple areas where this theorem would be used. So cryptography, which is a method to actually secure your information with the help of passcodes. So there you can use this concept. I hope you're clear with it. So finally, I would want to tell you that this particular theorem, it is been proved by Carl Friedrich Gauss. Now he was a renowned mathematician of his time and he is also called as the Prince of Mathematics for his marvelous contributions to field of mathematics. And you know, he is among those he is one of those three great mathematicians of his times, out of which we have Archimedes and Newton. So Carl Friedrich Gauss, or we also know him as Gauss. So Gauss, Archimedes and Newton, these are the three great mathematicians of their time, out of which it is Gauss who has given the correct proof for this theorem. So by this we come to the end of this lecture, which included, you know, the fundamental theorem of arithmetic. We learned its statement. We did the factorization problems using this theorem. Then we moved on to calculating HCF and LCM. We also learned the property of LCM and HCF. We did see the application of this in math, that is this problem. Of course, this is all also considered as its application in mathematics. And finally, we also saw the real life application of this theorem. So with this, again, we come to the end of this lecture. Thank you all for visiting my channel. Thank you.